To illustrate how powerful a lot of the Go concepts are, such as channels, Go routines and interfaces, I've got a 62-line program here which is actually a scalable work system. So what it can do is read line by line from standard in a list of jobs to do, and then run those jobs in parallel, collate the output and output that on standard out. And all of that is in 62 lines. It makes use of Go routines, channels for fan out, interfaces for defining how work can be done. And I'm going to show you how it works, then we'll make an actual program using it that does something. So first of all, I've defined an interface called task, and a task is able to do two things. It has a process interface, so a function which is called to process that task, do whatever is actually needed. And it has a function called output, which is used to write the output. So it will actually send out the output. There's also an interface which I call a factory, and that is a thing that can create a task given some string. And that will actually be a string that's received from standard in. So the idea is this program will read from standard in, call create in your factory, make tasks, and then run them in parallel, and use output to get the output. So let's look at how this operates. So the run function takes a factory, which is an interface, and it runs a couple of Go routines. So the first Go routine is using buff.io new scanner. Now the buff.io scanner is a very nice thing. Let's bring that up here. So there's a scanner, which is a thing for receiving essentially new line delimited pieces of text, and it wraps all the usual things you do for reading. It doesn't actually scan fields out, that's up to you, but it gives you the line by line. And you just make a simple for loop like this. And each time that for loop is called, if there's a line available, it'll be available here in s.text, and you can do something with it. And in this instance, what we'll do is we will call the create method on the factory that we have to create a task and pass it down a channel. And that channel is this guy. It's a channel of tasks. So there'll just be, this channel will get filled with tasks to do. And it's an unbuffered channel, so somebody will obviously have to be willing to do that, to handle that task, before that can actually be transmitted. If anything goes wrong, then we'll send an error, and when we're done, we close that channel to say there's no more work. And I'm using a wait group to count Go routines just so I get clean termination at the end. So I've created a wait group. For every Go routine I add, one Go routine, and every time one terminates, I call done. Now to do the work, I actually need some workers. And I've hard coded in here that I'm going to create 1,000. So I'm going to create 1,000 Go routines. And I'm going to use the wait group to count them. And each of these Go routines is really very simple. It's going to pull a task off of the input channel in. That task is T, and if you remember that task is an interface that has a method called process, so for each task it is going to call process to do whatever that task requires, and then it's going to output that down an output channel. So what's going to happen here completely naturally in Go is load balancing across 1,000 Go routines. So 1,000 Go routines are going to try and listen on in, that's what this range in does, and one Go routine, this one that's reading standard in, is going to write to in. So imagine 1,000 Go routines start, somebody starts writing and they just get picked up automatically as there's work to do. And when in is closed, then what will happen is this will terminate, this loop will end, we'll call done on the wait group, the Go routine will terminate. So as soon as we close the in channel to say that we're done, there's no more work to be done, all those Go routines will terminate. You also have a separate Go routine here, and it's waiting for all of the Go routines to terminate, and then it closes the out channel. And what's happening in the output is, finally the program reads from the output. So you can imagine now this is the fan inside. Those 1,000 Go routines are all writing to the channel, and this output will output all of the output from all of the tasks that have been processed. So right here, if you just implement your factory and your process and output methods on some type, then you're done. You have something that can scale. Obviously 1,000 is hard-coded. It could be any other number. We could use the flag package to set that, and typically you might want to do that because you might want to control how many simultaneous tasks work. But really, in 62 lines here, you've got something which could be quite complicated to write in another language. There's no explicit synchronization. There's no need to worry about how that's going to work. There's no load balancer. That's all part of the program itself. So now that I've got this flexible work system here that can scale up or scale down, let's do something concrete with it. And what I'm going to do with it is accept on standard in a list of URLs, web pages, go get those web pages in parallel and output whether this was successful or not, so whether there was any sort of error getting those pages. And to do that, I'm going to have to define a task and a factory. So the task I've started here, the task is going to have a URL, that's the URL to get, and a Boolean which indicates whether getting that page worked correctly. And then you've got a couple of functions you've got to implement. The output function is going to be pretty simple. I'm just going to print out the URL and I'm going to say truth value, did it work or not? And the process function is a little more complicated. We're going to have to do some network stuff here. So we can have a look at, in the net HTTP package, there's a really nice little function called get. And what get does is it gets a URL, gives you a response and an error. So I'm going to use that. So I'm going to import that up here. So when we're processing a task, we're going to say response error equals HTTP get the URL. And well, if there's any sort of actual error occurs, then clearly things are not okay. And we're going to return from there. And then we're going to take a look at the response, because anything other than an HTTP error 200 we might indicate as a problem. So we're going to have a look at that, and let's just use GoDoc to look at that. So the response structure actually has the status code here as an integer. Okay, we can do that. So we can say response.status code equals 200. And in fact, within the net HTTP package, there's actually nice defines for all those things. You can find in here this. So let's be good programmers and not use magic numbers. So status okay. So if it's okay, then we're going to set it to true, and we'll be done. Otherwise, we can set it to false explicitly. It's a bit unnecessary to do that because the fact that by default it will be false, but there you go. So that's the process side of things. So an individual task can be processed like that, and because it supports process and output, it's a task. And now all we need is a factory, and if you remember, the factory is the thing that's going to read from every line. So let's just make one of these. This isn't going to be very interesting because it doesn't have anything really to do, but I'm going to define a function on it. And that's, remember, it's this thing, create. So I'm going to get a line given to me, and I'm going to return a task. And in this case, I'm going to return an HTTP task. So we're just going to say task. And let's do this. So fairly simply, we're going to say, let's create an HTTP task, set its URL to be equal to the line, and return it. Okay. Doc. Okay. I'm going to need to, let's see if we can type things correctly, and I'm going to need format as well. Okay. So that compiles nicely. So now it's just a question of hooking this whole thing up. So we're going to say run, and the run thing requires a factory. So let's make ourselves a factory. Okay. Okay. So that guy's running. So it's running now, waiting for some input. So let's actually try something out. And in fact, let's just build it as a program, and then let's go down. So it went off and did that. It started 1,000 Go routines. It ran the whole thing, and it managed to get that particular page. So that's good for one thing. Now let's have a look at doing something like this, and that one false, because in fact that would have created a 404 error on that particular web page. But what would be more interesting is if we had a number of URLs. So let's just make ourselves a quick little file here. And okay, so Okay, so there's some files, and we can do this. And so out they come as it works its way through these things. See if O'Reilly. Okay, so there they all are. Now, those will all run in parallel, but we could actually slow things down. Let's just change this to only have one routine. And now it's going to have to do them one by one. And this would be much more obvious with many, many thousands of URLs. So just to cheat a bit, I'm going to do this. Okay, let's clean this up. All right. So we've got all those blank lines, but let's just in here. If the URL is blank, then we'll just give up like this. If h.url equals blank, then so that way in case there's anything silly in the data, and let's build it. So now it's going to go through fairly slowly because it's still doing only one at a time. So let's do this. Let's say there's a value n. Let's just stop that because it's going to spend a while doing that. And let's make n be the number of things that we're going to run simultaneously. Let's use the flag package. And right, let's say count. By default, 10 of those. Number of workers, like that. And n equals star count. So we'll just say whatever that is, and then we'll be able to use that here, within here. So, okay, so go back to that. Now we've got 10 running, so you can see things are spinning along a bit faster. And what I can do is I can go in here and say count equals 1,000. So now it's running 1,000 Go routines simultaneously and running through those things as fast as it can. As you can see, some sites are actually faster to reply to us than others, so it's actually done everything in the entire list that was in there. Let's throw in a bad one, just to make it a bit more interesting. So you can see there it was right there. And you can see it's running them in pretty much any order, right? They're coming through and just getting executed as they're available. So 62 lines of code, and you've got a completely flexible system. You could obviously change this to not take from standard in, but the basic concept is here. And in fact, this program I've used hundreds of times for different purposes because it makes a very, very quick parallel system. So if you looked at the output from before, you might have been surprised that everything seemed to be in order in some way. All the Cloudflare was coming first, and I think it was Google and O'Reilly and Yahoo. And you may have been wondering if there was some sorting happening inside. In fact, the ordering is coming about because of the speed of those relative websites. And to find that out, I can actually change the program a little bit. So what I've done is I've added to the task a couple of other values. These are time durations. One is elapsed, which will be how long it actually took to get the web page. And the other one is start, which is when did this particular task start processing. Now it should be the case that given the number of URLs we have and we have lots and lots of workers, they should all start pretty much at the same time. And then what I'm doing is when I output it, I'm going to say when did it start relative to the beginning of the program, and also how long did it take to run. So if we just build that. Oh, and also I keep track of when the program started here, and when the factory starts up, I keep track of what the time now is. And so if we do that, and then go back and run through those URLs, all with 1,000 workers, we can run through. And again, you can kind of see the ordering. So they started around between 3 and 6 milliseconds into the start of the program, various things started running. So they all started running within a few milliseconds of each other, a couple of milliseconds. But the times to actually finish downloading them varied a lot. So for Cloudflare, it was mostly in the sort of 400 to 600 milliseconds to get the complete page. Google about a second, O'Reilly a little bit longer. You can see there was one Google that was long there, Yahoo a bit longer, etc. So the ordering actually came about just because of the speed of downloading the pages. And you can see the faster the page, the nearer the beginning it was. But looking at the timings here, you can see that it was running simultaneously, that all of those requests at the same time were executing with really no effort on our part.